So what we are going to do is we are going to use those four simple rules that I introduced to you all on, if today is Friday, I think that was Wednesday. Sorry that I never know what day of the week it is. To develop some general relationships for op-amp circuits that you might see a whole heck of a lot in industry. So the first circuit that we're going to look at, we actually analyzed the other day. So if we have a circuit like this, where we have the non-inverting input terminal at ground, a feedback resistor, which I'm going to call R2, placed between the inverting input terminal and our output node, where we measure V out, a resistor R1 here, and some input voltage V in here. Can we develop a relationship that relates the input voltage to the output voltage for this generic circuit? Okay, that's our ultimate goal here. If we can do this, then we no longer have to analyze circuits that look like this, because we will have a very strict and straightforward relationship between the input and output voltage. Okay. So if this is the voltage V plus found at the non-inverting input terminal, what is it? 0 volts. And our voltage here, V minus, at the inverting input terminal, what's that? 0 volts. 0 volts. So if I apply Kirchhoff's voltage law at my, why does it just say there can now see it? Hopefully they've been able to see it the whole time. So if I apply Kirchhoff's current law at this inverting input node, what I'm going to get is negative Vn divided by R1 minus the out divided by R2 is equal to 0. Everybody okay with that? I can rearrange this guy slightly. And what I get is that V out is equal to negative R2 divided by R1 times Vn, which will be true for every circuit that looks like this. Okay. So this is called an inverting amplifier. Just a moment, please. So my first equation here, where I say that V plus is equal to 0 volts, is from doing step number 2, where we apply the rule that no current flows into or out of the input terminals of the op-amp, and then determine the voltage present at the non-inverting input by whatever means is necessary, which in this case is direct inspection. The non-inverting input terminal is connected to ground, and so V plus has to equal 0 volts. The next equation, V minus is equal to 0 volts, comes from applying op-amp rule number 2, which says there can be no potential difference between the inputs. So if V plus is 0 volts, V minus has to be 0 volts. My third equation is from applying Kirchhoff's current law at the inverting input node. And my fourth equation is just from simple algebraic manipulation of equation number 3. Okay. So this guy is called an inverting amplifier. And Eli, I believe, asked last class why it's called an inverting and a non-inverting pin. So in an inverting amplifier, where the input signal is applied through a biasing network, If we apply a positive polarity input voltage, our amplifier inverts the polarity of the output signal, meaning positive voltage in gives us negative voltage out, negative voltage in gives us positive voltage out, and it's scaled by what's called the amplifier gain. So our amplifier gain, AV, is simply the ratio of the output voltage to the input voltage, which in this case is just negative R2 divided by R1. So now we can say, if we have any particular input signal connected to one of this type of amplifier, those two resistors tell us exactly what the output should be because we have a simple relationship. Okay. Any questions on this guy or the analysis or anything? Hopefully fairly straightforward with just the steps that we used last class, right? So let's change things slightly. We're going to have a nearly identical circuit, but there is a very key difference here. So we're going to have that same feedback resistor R2 connected between the inverting input terminal and our output terminal. We are going to have that same resistor R1 here. But now, instead of applying our input voltage at that leftmost leg of R1, that's where we're going to apply ground. And now we're going to apply our input signal, Vin, at the non-inverting input terminal. So let me see if I can scroll and get these two circuits on screen at the same time. There we go. So literally the only difference between these two circuits is that we have swapped where we apply ground on the input side and Vin on the input side. We've just literally changed those two things. I'm harping on this because you guys are going to be asked as part of your lab assignment to create a non-inverting amplifier, which is what we're about to talk about, and an inverting amplifier. And I am trying to impress upon you that you do not have to completely deconstruct your circuit and rebuild it. If you wire things up correctly, you can literally change two wires and go from one circuit to the other and save yourself a ton of headache. Okay, so I'm just trying to impress upon you that this circuit on top, the inverting amplifier, and the one that we're currently analyzing are virtually identical, except for that one small change. In the top, we apply the input voltage on the leg of R1, and we apply ground at the non-inverting input terminal. On the one on bottom, we apply ground on the resistor R1 and the input signal to the non-inverting input terminal. All right. So we're going to analyze this guy in much the same way. So what is the voltage V plus, which is the voltage present at the non-inverting input terminal? Vn. So from that, what's this voltage V minus present at the inverting input terminal? So when I apply Kirchhoff's current law at my input node, what I get is Vin divided by R1 plus Vin minus V out divided by R2 is equal to 0. And if I mathematically rearrange this expression, I find that V out is exactly equal to 1 plus R2 divided by R1 times Vn. This guy is called a non-inverting amplifier. And it is a non-inverting amplifier because it does not invert the polarity of the input voltage, right? So a positive input voltage yields a positive output voltage. A negative input voltage yields a negative output voltage. Now, let's take a moment to discuss, actually, let's figure out what our gain should be here, and then we'll take a moment to discuss things. So what's the ratio of V out divided by V in for this circuit? Yes, exactly right. 1 plus R2 over R1. So if we're just looking at these two voltage gain equations, we can notice a few things about how these amplifiers might be used, okay? So our non-inverting amplifier, what's the smallest gain we could ever get? 1, right? If R2 is much, much smaller than R1, we get a gain that is very close to 1, okay? So our non-inverting amplifier can only be used to make signals larger. Our inverting amplifier, we can both make signals larger, so we can amplify things, or we can make signals smaller, right, by making R2 smaller than R1. So we can both amplify and attenuate. But while we have that increased functionality, it comes with the drawback, which isn't actually a drawback, of changing the polarity of the output voltage system, right? So we can make signals smaller, or we can make them as large as we want, but we're also always going to make them negative. The next circuit that I want to look at, I have enough room here, I'll do it on the next page. It's really kind of a combination of both of these. So let's say that I have this guy. I'm going to have a feedback resistor, and this time very specifically, I'm just going to say that it has a resistance of R. I have that resistor R1 placed between the inverting input terminal and something else that is also going to have exactly a value of R. So those two resistors right there are identical. Down here, I'm going to have another resistor R between the non-inverting input terminal and ground. I'm going to have a fourth resistor, also R, between the non-inverting input terminal and something else. And now I'm going to apply my input signals. So I'm going to say that my input V1 this guy here, connected through a biasing network to my non-inverting input terminal. And I'm going to say that I have a voltage here, V2, connected between the leg of this resistor. And it's applied through that resistive biasing network to the inverting input terminal, okay? So we have a couple of different, and the last thing obviously here is our voltage V out measured at our output pin. So there are two ways that we can analyze this. The first way is to do exactly what we've been doing. It's probably the way that I'm going to do it. and we will get a result. The second way, which honestly might be a little bit easier, is to apply the principle of superposition. Okay, but since it's been a hot minute since we've done superposition, let's talk about that first way that I mentioned. So what is the voltage here at the non-inverting input term, right? We need to apply the rule that says that no current can flow into or out of our input terminals, and then determine that voltage V plus. So what do I have? Anybody but you? Well, I already heard say the right answer. Half of V1, exactly right. So that means the voltage present at the inverting input terminal here is what? Also half of V1. So when I write my Kirchhoff's current law equation, what I get is 1/2 of V1 minus V2 divided by R plus 1/2 of V1 minus V out divided by R is equal to 0. So for this one, the algebra isn't quite as obvious, so I'd like for us to talk our way through it. What happens if I multiply both sides through by a factor of R here? I get rid of my denominators, right? Which means I'm going to have 1/2 V1 minus V2 plus 1/2 V1 minus V out. I can combine those two 1/2 V1s together, giving me V1 minus V2 is equal to V out. So this guy is what's known as a differencing amplifier. Because it gives me the difference between the two input voltages. Which may be useful. Any questions on the analysis of this guy? So I have what is effectively a simple voltage divider circuit. So let me explain it. We know that this current here that I've drawn in red is exactly 0 amps because ideal op amp rule number 1 says it has to be, right? So if I draw the current that's leaving this voltage source V1, I know that all of that current will flow through resistor R, and then all of it will flow through this second resistor R before it flows back around like this. So I have a voltage drop of V1 that's being divided among two identical resistors. So the voltage drop over the resistor connected to ground has to be exactly 1/2 of V1. I can get that using voltage division, which I can apply here because the resistors behave like they're in series because no current can branch off. Or I could get the exact same result by applying Kirchhoff's voltage law around the loop that I've drawn here in blue, with the understanding that the same current flows through all of those elements connected in quotation marks series. Any other questions about this guy? Differencing, taking the difference of those two signals. Let me draw that C better, Joy. I apologize. Differencing. Maybe that's better. All right. This guy right here that I'm about to analyze is effectively a specialized version of the inverting amplifier. So let's say that I have some resistor here, and I'm going to call it RF in this case for feedback resistor. And now I'm going to connect several resistors to my inverting input node. So let's call this guy R1, this guy R2, and this guy R3. And because I have chosen poorly, let's say that we apply a voltage V1 to this pin, a voltage V2 to this pin, and a voltage V3 to this pin. So I'm not drawing the voltage sources explicitly because I didn't leave myself enough room. But consider all of those voltages, V1, V2, and V3, as nodal voltages measured with respect to ground. Here is our output, the out. What is the voltage present at the non-inverting input terminal anode? Zero, because it's connected directly to ground. Alan, what is the voltage present at the inverting input terminal? Exactly right. V minus will always be identical to V plus for these negative feedback op-amp circuits. So what I can do now is apply Kirchhoff's voltage law, Kirchhoff's current law at my inverting input node. And what that tells me is that I will have negative V1 divided by R1 minus V2 divided by R2 minus V3 divided by R3 minus V out divided by RF is equal to 0. And rearranging, I find that V out is equal to negative RF over R1 times V1 plus RF over R2 times V2 plus RF over R3 times V3. This guy is what's called a weighted inverting summer. The inverting portion comes from the fact that I have a negative sign out front. So any positive input signals I apply are going to wind up giving me a negative output voltage. It's weighted because each of my input signals gets weighted by a different value depending on the value of the resistor connected to it, right? So if R1 is smaller than R2 and R3, the contribution of that input signal V1 is weighted differently than the other guys, right? And it's a summer because the output voltage depends on the sum of those weighted voltages. Positive polarity on top, negative polarity on bottom. So effectively, this guy is inverting because there's a negative sign out front. So if V1, V2, and V3 are positive values, the output voltage will assuredly be negative. So that's where the inverting comes from. Kobe. So gain becomes a difficult quantity to think about when there are multiple inputs, right? Because for our inverting amplifier and our non-inverting amplifier, there was a simple ratio because there was only one output voltage and there was only one input voltage, right? For our differencing amplifier, we had two input signals. So it's very hard to classify the gain like that unless we classify it to each signal. And the same thing here, right? When there are multiple inputs, we're never going to have a standard gain equation. Gain is the ratio of the output voltage divided by the input voltage. That's it. So when we have more than one input, can't really do it. Good question though. So what change would I need to make to this circuit to make it just an inverting summer? Effectively, how do I make it where all of the inputs have received the same weight or scaling factor? Yeah, just make R1, R2, and R3 equal. And then everything is amplified by the exact same amount. So it just adds the voltages together and amplifies it by a factor of negative RF over R1, 2, or 3. All right, so in 30 minutes time, actually a little bit less than that because I got here late, we have learned that op amps can scale signals, meaning make them larger, attenuate signals, meaning make them smaller. They can be used to add signals together, and they can be used to take the difference of signals. Now, I want to introduce circuits containing op amps and capacitors specifically, so that I can show you how we can do calculus with op amps as well. Yeah. Yay, indeed. Yeah. So multiplication and division you can't do with just one op amp. So we're not going to cover those because we are not. Yeah. I thought you were talking about the mathematical operations of multiplication and division, which are absolutely signal processing steps. You just can't do it with one op amp. All right, so let's say that we have the following circuit. We have a capacitor here. We have a resistor here. And this is going to be our input voltage, Vn of t. So the first thing that we can observe about this guy is it's practically identical to our inverting amplifier, except that we now have a capacitor in our feedback path. Okay. So as a quick reminder, and I want to be very clear here, I absolutely expect you guys to have, I hesitate to say memorize, learned these relationships for Monday's test. We know that the voltage drop the voltage drop across a capacitor, Vc of t, is equal to 1 over c times the integral from negative infinity to t of IC of x dx. And similarly, we know that the current flowing through a capacitor is C dV by dt. Yes. Okay. So what I'm going to do just real quick, because this is going to help us. We are effectively going to employ the same techniques that we've been employing, but we're going to have to think about things in a slightly skewed perspective, okay? So what I mean by that is, let's say that this is our capacitor voltage Vc of t, and this is our current capacitor current IC of t. Okay. So what is the voltage present at our non-inverting input terminal? 0 volts. Which means the voltage present at our our inverting input terminal is also 0 volts, right? I'm going to draw an arrow here, just call this guy 0 volts. So if I apply Kirchhoff's current law here, what I am going to see is that negative Vn of t divided by R plus IC of t is equal to 0. All right. How can I relate my capacitor voltage to either Vn or Vout? Anybody have any thoughts? This is where things are going to get a little, the level of difficulty is increased slightly. Ian, what are your thoughts?
So if we know that there's no voltage, if we do like KVL, starting from the non-inverting input, we have 0 volts, we see VC of t, and then we get the V out. Okay, the VC of t plus V out equals 0.
Exactly right. Okay, so the suggestion here, which is 100% correct, is that if we apply Kirchhoff's voltage law starting here at ground, we go here, and then we come back around here at ground, what we get is VC of t plus V out of t is equal to 0, which means VC of t is equal to negative V out of t. Is everybody okay with that? Right? Just an application of Kirchhoff's voltage law. So I'm going to revisit my Kirchhoff's current law equation. And I can say that negative Vn of t divided by R plus C dVc of t by dt is equal to 0. Actually, that's not the relationship that I want here. Let me think about this for just a second. No. Okay. We are going to use that relationship in blue, but I'm not going to use this one I just wrote. We're going to approach it in a slightly different way. We can say that IC of t is equal to Vn over R, right? Just simple algebraic manipulation of our KCL equation. And therefore, V out of t, which is equal to negative Vc of t, will be equal to negative 1 over c times the integral from negative infinity to t of Vn of t divided by R dt. So I'm using my integral-based relationship here. And I can simplify this further and say that I have V out is equal to -1 over RC times the integral of my input voltage. So this guy is what's called an integrator, because the output is an integral of the input signal. So how this guy is very commonly used, and part of it is in this board here that we're going to be using. If we put a square wave as an input signal, we get a triangular wave as an output signal. Right? So this is a functional part of what are called analog wave generators or function generators. This is also a huge deal for those of you who are pursuing electrical engineering or maybe wind up choosing to go into ICE-T. This is a huge part of control systems engineering, this integrator. And as it turns out, it's also a filter. This one circuit performs multiple roles depending on the type of signal that we input into it, okay? So the last circuit that I want to analyze is the exact same thing as this previous circuit, except that we switch the resistor and the capacitor. So previously, excuse me, we had the capacitor in the feedback, so let's put the resistor in the feedback this time. Here is V out of T. Here's our capacitor C. Here's the N of T. So this is going to be my capacitor current, IC of T. This is going to be my capacitor voltage, VC of T. All right. So what is the voltage present at the non-inverting input terminal? 0 volts. Oh, goodness gracious, I drew this not remotely correct. Yep, I'm sorry about that. This should be connected to the inverting input as well. I have made a total boneheaded mistake there. Yeah. My apologies. Yeah, now it actually does something. The other way around, we just sank voltage drop across the capacitor to ground. Did nothing, not an amplifier in any shape or form. I apologize for my boneheaded mistake there. So our voltage present at our non-inverting input terminal is 0. The voltage present at the inverting input terminal must also be 0. We apply Kirchhoff's current law at our inverting input node. What we'll find is that we have negative IC is equal, or excuse me, plus, let's see, negative IC plus negative V out divided by R is equal to 0. And so I'm going to slightly rearrange this and say that IC of T is equal to V out T over R. All right, so how can I relate that capacitor voltage to Vn in this case? Because the capacitor is connected to the input side of our circuit. Not you, somebody else. Brandon, you're a smart fella. How do I relate Vn and VC.
Could we do the same loop, but whenever we go to our like step 2?
So let's do KVL around this loop right here. Right? We start at ground and we end at ground. That's an agreeable loop. So what do I see first? Negative Vn as a function of t. What do I see next? And then that's equal to 0, which means Vn and Vc are the same quantity. So I can use my derivative-based relationship now. And what I will have is negative C d Vc by dt is equal to V out divided by R. So what I'm going to do now is just multiply both sides through by R and replace Vc with Vn. And this gives me negative Rc times the derivative of Vn is equal to V out. So this guy is a differentiator because the output signal is a scaled version of the derivative of the input signal. So if by chance we had a triangular wave, we could make a square wave out of it. This is also, so this one is going to be a low pass filter because the other one was a high pass filter. And this is also used extensively in control theory. Yes, Joy. No. So that's a fantastic question. These circuits that I've introduced today are useful if you spend a lot of time analyzing op-amp circuits. In this class, I would say that you guys don't qualify for them, okay? So if you learn these and memorize these, you can save yourself a minute or two of analysis, absolutely. But if you apply those simple 4 steps to analyzing negative feedback op-amp circuits, which is how we got all these results, you will be able to analyze any and every circuit available on your exam, for sure, okay? So I'm not in any way trying to say that you shouldn't learn this or memorize this, because a lot of you will wind up using op-amps in practice for your senior design and all that kind of stuff. If you're in biomedical engineering, mechanical engineering, all that kind of good stuff, these are going to come bite you in the butt again. So it's useful to understand them. But with regards to what you're going to be tested on, I'm not going to say, how do you know, what type of circuit is this? That's a waste of your time and a waste of my time. I'd much rather you be able to analyze them correctly than tell me what their names are. Is that fair?